for the LIGO control systems, working on an automated follow-up pipeline for use with outliners produced by All Sky Semi-Coherent Continuous Wave Researcher from the 2009 to present. He has also developed and continue to improve a digital camera. He has a very great experience in designing and improving the different types of the camera, like digital camera and some other cameras like phase camera, etc. And he has performed a search aimed at the crab pulsar, assuming its gravitational wave frequency, which is not exactly twice the electromagnetic pulse frequency. And the most importantly, he has helped to verify the calibration of the data from LIGO's fifth science ROM from the 2007 and 8. He has a significant and a number of presentations in the different scientific gatherings like the WAVE meeting, La Jolla, California, and in the Plaza Hotel, Puerto Rico, improvements in the wideband directed sources for the LIGO. Similarly, he has in the August LSC meeting. So this kind of very significant meetings, he has presented his work. So finally, he has a number of the dozens of or more than dozens of papers, significant papers in the publication sites. So such as a significant publication in the Physical Review, Letters, Nature, Classical, Quantum, Gravitational, Nuclear, Instrument, Methanol in almost all the, in almost every years from the 2001 to current. So we are very honored and we are very happy to have you, Dr. Joseph Betzwieser, as today's speaker. Welcome, Dr. Betzwieser, for your presentation.
Thank you very much for that very kind introduction. Appreciate it. Okay, so unfortunately, we had a slight change of plans. We originally planned to do this from the control room at Livingston. However, due to the weather and potential tornadoes, we've been sent home. So I'm unfortunately doing this from my house. So please bear with me as we do this. Okay. Hopefully we don't lose power due to the storm. All right. This is going to be a brief introduction to the LIGO detector. I'm making the assumption people are familiar with gravitational waves from the rest of the conference. And I don't need to go into that, but this is going to be on the hardware, the detector itself, that actually makes the measurements that produce the data that is then analyzed and used to look for gravitational waves and so on. So without further ado, let us get on. So the first is welcome to Livingston, Louisiana. This is an aerial shot of the LIGO site in Louisiana. The things you can take from this are the site is very big. The arms are 4 kilometers long, and you can kind of see the scale of the cars relative to the size of the site itself, which kind of disappears off into the distance. The other thing to take away from this is we're kind of in the middle of nowhere. We try to be away from lots of seismic motion, like lots of traffic, lots of like city type stuff. So we're kind of located in the middle of a logging forest, actually. This is all to isolate the instrument from ground motion and everyday life. Okay, so what is LIGO? LIGO stands for the Laser Interferometer Gravitational Wave Observatory. So the way we make the measurements is via interferometry. And so this video is going to show a kind of a brief idea of how that works. What you do is you take a laser beam and you split it through a mirror. So you get equal beams going down 2 different arms, reflect them back. Now, if the distance that laser beam has traveled is different, then you start to get bright dark fringes. So you can imagine light as a wave. You got the high points, that phase front propagating to the mirror, reflects off. If the phase front is out of sync by half a wavelength, you get no light coming to the photodetector, and all the light actually goes back towards the laser. So then if you change the path length, so if a gravity wave passes and shrinks one arm and lengthens the other, or vice versa, you start to get this bright dark pattern at the output where the photodetector is. So as a gravity wave passes, it is detected by how much light is reaching a photodetector at the output port of this interferometer, which is interfering the light from the two arms. So that is the fundamental measurement, that you have a gravitational wave, which is a transverse shrinking and stretching in 90 degrees apart, traveling transverse, that shrinking and expanding is transverse to the direction of motion. So you can imagine a gravity wave coming straight down, it would make those arms longer one direction and shorter the other, and thus produce the signal. Now, a simple interferometer is not sufficiently sensitive to actually measure a gravitational wave, because the motion, the differential motion, is just so small. So we have to use a lot of tricks. We have to make it more sensitive in a lot of ways to be able to detect these gravitational waves. So not only are we a simple Michelson interferometer, we're actually let's see if I can get this to move on. We're a dual recycled Fabry-Perot Michelson interferometer. So let me go through that. So this is a schematic diagram of all the optics in the advanced LIGO detector. And what we have here are what we call Fabry-Perot arms, which have both a mirror at the end station, that reflection mirror, but we also have an input mirror, which was not shown in the previous graph. This mirror has a reflective side facing the end. So this laser beam comes through, goes to the end, reflects off, it comes back, and then reflects back again. So if you imagine this mirror being 99% reflective, on average, you get 100 bounces between these before the light leaks back towards the beam splitter and then making the interference measurement. So what this lets you do is, instead of having that laser beam sample 4 kilometers of space-time, so where that gravity wave is affecting it as it travels for 4 kilometers, it's more like traveling 400 kilometers, and you're sampling a lot more space-time, so you're much more sensitive to it. So the laser beam path picks up more of that gravitational shrinking of one arm and extending of the other arm. So the Fabry-Perot arms are a way to make the 4 kilometers seem much bigger as the light travels by basically reflecting it back. Now, I also mentioned, I should point out that the laser tends to interfere on a dark fringe. We actually set the lengths associated with the Michelson interferometer to a dark fringe, so there's very little laser light coming out towards the output, towards the photodetector, which means most of the light doesn't get destroyed, it gets reflected back towards the input laser. So what we want to do is capture that laser power. We don't want to throw it away, and we want to recycle it back into the arm, so we have more photons traveling down the arms, and so you sample more space-time with more photons. So we have these power recycling cavities. So this is basically a compound mirror whose entire job is to take the laser power that's rejected by the beam splitter and sent back towards the laser and push it back into the arms. So in this way, we can start with, let's say, a 60-watt laser. Our laser beam starts at 60 watts, comes in, and actually gets like a recycling factor of about 40. So you get 40 times 60 watts, and then you get an additional factor due to the Fabry-Perot arms, like storing the laser light by hundreds of bounces, and you wind up with hundreds of kilowatts of laser power circulating in the arm at any one time when we're making the measurement. So the more laser light we have there, the more photons are sampling that stretching and squeezing space-time, and makes it more sensitive. We also have a number of optics on the output side, which we call a signal recycling, or maybe a signal extraction compound mirror, whose job is to lets us change the frequency response of this detector to passing gravity waves. You can actually try to accentuate a certain frequency by making kind of resonant in here and become less sensitive to other frequencies, or you can try to make it broadband and try to optimize for gravity waves across a wide frequency range, which in our case is something like 10 hertz up to up to a few kilohertz. So it's we're actually listening or detecting in the audio band. You can actually listen to our data. So This dual recycling is power recycling, which increases the laser power, and the signal recycling, which lets us tune the frequency response of the signal that's actually eventually reaches the photodiode down here. In addition, we have other optics whose job is to clean up the light. Stray light or higher order modes can cause problems for the interferometer. So we like a nice round transverse electric magnetic 0, 0 mode. So a nice round Gaussian beam. And these optics here are kind of input, and optics here are output mode cleaners, which try to reject kind of higher order modes and stray light so that we get a nice clean beam at the photodetector for making the measurement. Okay, so each of these blocks representationally is actually quite complicated. So we've gone from a simple interferometer to like more optics, but each of these optics is also very complicated because we're trying to isolate it from the rest of the world so that the path length changes only from, let's say, the passing gravity wave and not due to the fact that there's some truck driving by nearby. The way we do that is through isolation stages, which we have 7 stages of isolation. So what we have is the first passive stage is a pendulum. We literally hang our mirrors by glass fibers or metal wires because a pendulum is a nice natural isolation system, basically above the resonance frequency. In our case, about a hertz. So above a hertz, you get about 2 orders of magnitude for every order of magnitude in frequency. So at 10 hertz, we have a suppression factor of 100 from this pendulum, then another 100 from here, and then another 100 here, and another 100 here. So you have less motion at 10 hertz by about the ground as it shifts by about a factor of 10 million, 10 to the 8. That's why we hang this to isolate the mirror from nearby motion. This is then suspended from our internal seismic isolation system, our ISIs, which is like weighs about a ton or 2. And this is an active system, which has coils and magnets and stuff, and can move 2 stages independently of each other so that we feed ground motion sensor data. So we measure the ground motion, we feed it to the system. So when the ground moves to the left, this system moves to the right and cancels the ground motion at low frequencies below the resonant frequency of the pendulum, where we don't actually get any isolation. Then this is all set on top of hydraulics, which gives our largest actuation, but very, very low frequency. We need that actuation for things like tides. The same way the moon creates a tide on Earth, like pulls on the ocean, it actually pulls on our mirrors too. So we need to actually move the whole system to account for the fact as the moon goes around the Earth today, basically. We have to account for that, and we push that off to our hydraulic system. So when this is all installed, this is what it kind of looks like. This is our ISI system, which is supported by piers, which connect to our hydraulic system outside the chamber. And then this is that suspension cage hanging here. And this is the actual optic in situ that the laser beam is bouncing off of. And then this other chain behind it, this reaction mass, is actually how we control the pointing. In order to get the laser beam to bounce back and forth 4 kilometers away, we need to very precisely steer this mirror. So we actually paint a metal pattern in 4 quadrants on the back of this thing and also on the reaction mass. And we put a voltage on the 2, and we can push off each other to aim this mirror. So this mirror gets pushed back, this one gets pushed forward, or they get attracted, and you can aim this mirror just by this electrostatic attraction. And it's basically pushing off something very quiet because it's suspended and isolated from the rest of the ground like this. In addition, you notice this is in a big chamber. This chamber is actually part of a giant vacuum system where we pump all the air out. We get down to something like 10 to the minus 9 torr. So we pump all the air out because you don't want the laser light scattering off the air molecules or bouncing off this mirror and kind of moving the mirror because of somebody's talking or something. So this is all pumped out of air when we're actually making the measurement. So this is all needed in order to get to this point, which is to create a time series of a gravity wave coming through. So this audio is from our first detection back in 2015, September 14th. So hopefully you'll be able to hear this. We'll see. See if it buffers. Okay, so pause that. Okay, so you can. I hope were people able to hear that? Hopefully. anyways, what this is showing is the time series. This is the time series of that changing length of the arms. So basically noise, and then you can start to see the oscillation, then they speed up and get higher frequency. The graph behind it is the frequency domain version of this, which is showing that it starts at low frequency, let's say 32 hertz, and then goes up to 256, 512-ish hertz at this high frequency. You can see it's starting to oscillate faster. And that time series is generated by that detection at that photodiode. And as you heard, it was kind of a chirp sound. The first one at low frequencies is the original speed, and then they sped it up to high frequencies to make it easier for certain people to hear. But the thing I want to also point out is you hear a rumble at the very beginning, like a bass rumble kind of thing for that very low frequency. That before the chirp is actually the noise of the detector, because the detector is still got some fundamental noise sources, which is producing motion, which is kind of hopefully random, but can be also influenced by nearby things. Hence our need to isolate as much as we can the mirrors from the rest of the world. And so yeah, so that I want to get into in a moment. But the other thing I want to point out is here we also have sister sites up at LIGO Hanford, and then there was also during observer runs there are other detectors, Virgo and Kagra. You need multiple detectors in order to be able to detect where the signal is coming from. Basically, this L pattern is kind of omnidirectional. You get a bigger signal if it's coming from, let's say, straight on, because it couples to the arms. If you imagine a gravity wave coming straight down on this L, one arm is getting shorter, one arm is getting longer, that gives you the maximum signal. If, however, it's, let's say, coming straight down this way, this arm doesn't change, but this arm is getting longer or shorter, so you get half the signal. So this graph is kind of showing it's coming in. If you're coming straight down the 45-degree, this arm is getting shorter at the same time this one is getting shorter, and then it's getting longer at the same time this one's getting longer. So there's no differential. So there's a null here. We can't actually detect a gravity wave coming straight in at the 45 degrees because of the shape of our detector. So this is a reason why you want multiple detectors in different orientations, but it also means we can't tell where a source is coming on the sky because it's confusing between its distance and its coupling factor with the detector. So we need multiple detectors, like 3 scattered around the world, in order to kind of triangulate where an event is coming relative to the detector. Okay, so that I wanted to get into, like the physics of how that wave interacts with the detector. So last in this talk, I want to show you what scientists stare at a lot. So this is a lot on this plot. What I just want you to look at is the blue line right now. Blue line is the noise of our detector. So we've converted from time domain signal, random signal coming out of the detector from various noises, and that converted to the frequency domain, produces this very structured graph. And all I want you to take away from this graph is there's a lot of physics underlying the noise that determines how well we can detect those gravity waves. The lower we can make this blue line, the less noise we have in the detector relative to the gravitational wave strain that's passing, the more signal to noise we have, and the more signals we can detect. But we're limited by a whole host of physics, of fundamental physics, as well as some engineering stuff that prevents the noise from going lower, that we're always trying to improve. That's our job as detector scientists working at the site, is to try to work on these noise sources that are hiding underneath the sum of all noises to make the detector better, which include things like electronics noise. The United States uses 60 hertz AC power, and that gets into all our electronics. We have this giant spike in our noise where we're not very sensitive because we have 60 hertz getting into all our electronics. We also have physical things like this represents the thermal suspension noise, like the fact that the fibers, when they get energy in them, ring like a violin or a musical instrument. So like a stringed instrument has natural frequencies. Our suspensions that I showed you have natural frequencies at 500 hertz, a kilohertz, 1500 kind of resonances, these spikes here. And so there's a whole host of physics that goes into determining how well we can detect those gravity waves as the chirp comes in through this spectrum. Okay, so I guess I should ask if there are any questions of this stuff so far before I try to move on to our recorded virtual tour section. or should I just go straight on to the videos?
Yeah, Joe, you can go ahead with the video and we'll take the
Okay,
question.
excellent. Okay. Why don't we start with the drone flight, because I think that's cool. So this is a recorded drone flight over our site. This is, I think this is the X end. So you can see a car relative to the end station when it has that end mirror. And then there's this concrete tube, which is protecting the metal tube, which has all the air pumped out, that goes for 4 kilometers to the site. So in the interest of time, I'm going to zoom into when we actually get close, because, well, it's maybe not so interesting flying 4 kilometers. So this is as we approach the actual corner station where the 2 arms meet, and where we actually make that interference pattern inside. We also have a science education center if you ever come out to the United States, which has all sorts of cool museum type stuff and exhibits. But this is kind of gives you a scale of how big this detector is. You can also see some structures out here which are interesting, these are liquid nitrogen tanks, which are used to help maintain our vacuum. If we lose power, that liquid nitrogen powers cold traps, which keeps our vacuum working, even though we don't necessarily have power. As you can also see, there's not much around at all. This is basically all forest land because we're trying to stay away from people as much as possible, and the motion that's due to them. Okay. So what I think I'm going to move on to next is the control room. Oops, let me start this at the beginning. So I'm going to try to take this kind of like how we do a tour at LIGO. So feel free to hand the microphone around if people have questions or want to talk about something in particular they see in here. So this is the control room where we actually run the instrument from, where people work on a day-to-day basis, where we have the data, we collect the data, and we try to make the noise better. And we have a whole host of auxiliary channels. We record something crazy like 200,000 different individual channels associated with this detector to make it work, because it's just so complicated. There's just so many little parts that make it work. And so we're just looking at the screens that as scientists and operators look at the most to see how well things are working and so forth, or operating. Unfortunately, this video was taken when we were not observing. We were down for some reason, I forget what, in this case. But here's the, yeah, so yeah, we weren't running, unfortunately. The next view over, it's going to move over to is that spectrum I was showing you. So we actually have this on the main wall, because that's what the scientists stare at the most, which is the frequency domain version of the gravitational wave channel. And that's what this screen is showing you, that noise curve that I showed you just a few minutes ago. Then we have various control signals for those various cavities I was showing you. So I was talking like the power recycling, signal recycling signals are here. They tell you how well they're, like if they're locked or not and so forth, or if they have power buildup and so forth. These cameras would be looking at scattered light off the optics, but at this time, I believe the laser was off for this particular video. So I'm wondering if people have any questions on the detector or the what they're seeing here. I can just start talking about individual screens or concepts in this room, if not. So I think the video is failing to buffer.
So
that might be all.
any questions you want to ask? Like, this is the actual control room where we work, right? So we control all the optics from inside the control room. So once the vacuum is sealed, we cannot control anything. So we just control everything from the control room, all the optics and everything. So the video we are seeing currently is when the detector was not locked. But when the detector will be locked, all these things will have like much more content to see. But if you still have any questions, I can pass the mic around and just raise your hand. I'll stop Joe, and you can ask the questions.
Yeah.
Go ahead,
yeah.
Joe.
Go ahead. Okay. Since I don't, for whatever reason, I'm having some buffering difficulties. I think I'm just gonna start talking about stuff. Nope. My network is not liking it. So let's see if I can refresh it. See if this works. There we go. Okay, so I'm just going to start talking about various stuff in here. So one of the things I'm very familiar with is the calibration of the instrument, which is what we were showing right about here. So we actually have something. One of the questions you can ask is when we say we can measure something down to like, I don't know, 10, like 1 part in 10 to the 20 meters or so, like how do we know how well we can do that? And one of those methods is to like set error bars on the gravitational wave channel is to use something called a photon calibrator, where we literally bounce a laser beam, a very small laser beam, so not the 200 kilowatts circulating power, but like a 2-watt laser, bounce it off the mirror and measure very precisely how many photons are bouncing off it with a well-calibrated photodetector. And then that induces motion in the mirror, because for every action, there's an equal opposite reaction. The photon bounces off the mirror and imparts momentum. Calculating the motion of that optic as a pendulum is then relatively easy from the extra force you're putting on. So you can oscillate the laser beam, how much amplitude you're putting on it, at, let's say, 100 hertz, for example. And then you can see that signal show up in the gravitational wave channel at 100 hertz. Since you know how many photons are bouncing off that mirror, you know how many meters of motion that pendulum has been forced to swing, and then you can calibrate the detector based on literally counting how many photons have bounced off of it. So that's how we actually calibrate the instrument when we say we're measuring like 1 part in 10 to the 21 or something of that 4 kilometers. And that's what these screens in the control room are telling us about right here, is the status of that photon calibrator system, the spectrum relative to the lines that are being driven by the photon calibrator and so forth. Also on these screens is the performance of those seismic systems I was telling you about. This is actually telling us about the seismometers, which are on top on those ISIs I was telling you about. So this is telling us about the performance of that seismic isolation system relative to the actual ground motion. So one of these lines is the ground motion, and then then you also have suppression below the ground motion by those seismic systems. In addition, we have cameras looking at various cavities and the pre-stabilized laser. So these images here on the bottom left are from the 70-watt laser that we run at about 60 watts. Actually, this would have been before they upgrade to 100 watts. So anyways, yeah, so these are telling us about the status of actually looking at the room where the laser, the heart of the interferometer, is working, and then pickoffs at various places, various cavities. This is just some digital control script. So that, like, we have, I don't know, at this point, probably tens of thousands of lines of code actually running the interferometer, and that's telling us kind of the status of the computer code that's running it. This is a fun graph because this is looking at when we're running. It's got the shot. Essentially, it's comparing shot noise. So the fact that photodetector has a quantum mechanical chance of detecting any given photon, and then and comparing that shot noise to the actual performance of the photodiodes strain sensitivity, and seeing if it's lying on the shot noise. Are we quantum mechanically limited by the noise associated with just detecting photons, or if we're doing worse than that, or when we're using a really cool device called a squeezer, where we squeeze the noise in the light that's reaching the photodetector, so we have it more, let's say, in the phase or more in the amplitude. If we're below the shot noise limit, because we put the noise into the quadrature, either the amplitude or the phase that we don't care about. So unfortunately, this particular graph is normally telling us how well we're doing. Unfortunately, we've been down, and so there was no range for any of the sites, or Hanford or Livingston. But normally that's our metric, is megaparsecs. How many megaparsecs out we could detect a signal to noise ratio 8 neutron 1.4 solar mass neutron star, 1.4 solar mass neutron star compact binary coalescence. These channels are telling us about the status of the basically actuation control system. So the electrical signals that are going out to those ESDs, those voltage controlled pointing of the mirrors is reported here. And then we have various cameras looking at cavities. So this would be the anti-symmetric port. So this would pick off this thing that goes to the photodetector that actually detects the final result. This is our mode cleaner, which is unlocked. So everything's reflected and there's nothing transmitting through it right now in this particular image. So basically, it's a lot of diagnostics about the health of the detector, which is very useful for an operator to say, okay, this is what we have to do to fix the interferometer. This is what we have to do to get it back to a running state. Okay, how are we doing on time? Okay, we got about 12 minutes left.
We can go to the ramp video then, maybe.
Okay, if there's no questions.
Any questions? No, 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 nope.
I'm doing a very good job, apparently, or a very bad job. I'm not sure which. Okay, so this is a video outside, kind of on the ground, looking down the arms. So this is a typical tour activity, which is to go look at the 4 kilometers down. Actually, I don't know if this video shows enough. Can I make this full screen? Yeah, maybe that'll help. But yeah, all I can say is you don't want to forget your tools at the corner station when you go to drive down there, because it's like driving to another city. It's that far away, several miles. And then all the support stuff necessary for an actual like scientific site to work, like that makes life nice, like air conditioning, water supply, and so forth. So yeah, I don't think this portion is not so interesting, but I guess as we can go into the building, I think that'd be about here. So going to the building may be interesting. But yeah. I mean, if there's no other questions, I could actually go into some of the more fundamental noise sources back on that noise plot, because I was expecting more questions from the audience. Yeah, there's a plaque here commemorating the first gravitational wave detection, which is kind of cool. But yeah, there was over 1,000 people involved in that, basically that first paper, that first detection. It was a real effort over 70, or let's see, 1970s till 2015. So it was like first proposed back in the 70s. So that's, what is that, 45 years or something crazy? It was a long effort to get to that point. And then I guess offices aren't very exciting, but it's your standard scientific have workplace. So yeah, this is what it feels like to go to work every day in LIGO. Okay, if there's still no questions, why don't I talk about some of the other physics I didn't go into earlier then?
Yeah. So Joe, yeah, we're almost at the end of time. So
Oh, we're at the end of time? Okay, good.
yeah.
All right.
Okay. So anybody have any questions regarding the detector or work experience in LIGO or anything? You can raise your hand. Sa ilay kay isod mo sa? Nope. 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 Okay, Joe. We don't have much of any questions at this moment, but I will take a session and maybe give them a brief introduction of what exactly we do. in the later hands-on sessions.
Okay, sounds good.
Yeah.
Yeah. Well, thank you very much for listening. I appreciate your interest. Okay.
Thanks, Joe.
All right, signing off.